Let's do one more calculus operation with this curve, and that's find an area. So I'd like to find the area within this whole loop. It's a very natural question to ask, and we're more used to finding areas of under curves or like curves compared to straight lines, and so it's a little easier first to get the area of this half, and then using good old symmetry, we can just double that. So the area of just this half, now it's a sideways area. It's the area between two curves where one is a straight line, and so it'd be pretty easy. It's just the integral dy. That's these widths of strips here, and the width of the strip is dy, and the length is just x. So if I had x as a function of y, our usual situation here is we do this kind of sideways integral with a dy is if we know x as a function of y. But it turns out, and of course that's not what we have here explicitly, but it turns out that it's fine because, remember, we can use a substitution, or we can use, again, the fact that dy is just going to be dy dt times dt. So one way to think about it is we sort of imagine we're going to set it up. We don't actually set it up because we don't have x as a function of y, and we do a change of variables. But we actually do that change of variables preemptively and say, you know what? Area is going to be the integral, and I'm going to use t as the variable. I'm going to use x. It doesn't matter where I get the values of x from. I'm going to get them from t. And the dy I'm going to write as dy dt dt. That's pretty cool. Or if you like, x y prime of t. Or if we're being more careful about functions versus variables, and this is how Stewart writes it, he would write it if x is f of t and y is g of t. That's a more careful kind of notation. It's going to be f of t g prime dt. But if you write x of t, y prime of t, I'm not going to be too worried about that. Okay, and then I need to actually have the right t values. As usual, if we set this up with a y going from 0 to 9, well, that's the right values for y, but with any kinds of kind of change of variables, we need the right values for t. Luckily, we found those way early, and that's going to be 0 to root 3. Okay, and f of t, remember here, is, excuse me, 3t minus t cubed. And dy dt was 6t dt. And I don't think I'll go to the pretty printing thing. I think I'll just finish it off here. Let's just go ahead. Let's put that up here. And that's going to be integral 0 to root 3 of, we're going to get 18t minus 18t squared minus 6t to the 4th dt. You know, that's going to get in my way. And so that's going to be 6t cubed minus 6/5 t to the 5th, all from 0 to root 3. We're going to get a slightly messy kind of answer. We're going to get, let's see, root 3 cubed is 3 root 3. And root 3 to the 5th is 9 root 3. So we're going to get, the root 3 comes out as a common factor, and you know what, I'd say over 5 as well, and that's going to be 18 times 5 is 90 minus 54, and so that's going to be 36 root 3 over 5. Ooh, and that's for half. If we wanted the whole loop, the whole loop is going to be 72 root 3 over 5. Now, again, whenever you're doing integrals, there's no guarantee that this is going to be a particularly nice function when you do this, but it's actually much more likely to be nice than the arc length calculation, because there's not a square root that's forced on you. It's just the product of f of t times g prime of t. And I did an example where it was integral x dy, and that turns into f of t g prime of t dt. But the great thing is there might be other situations where it makes more sense to do integral y dx, and that's going to be g of t f prime of t dt. They both work in the right situation when this is going to make more sense when you have this kind of picture between it and the y-axis. This is going to make more sense when you have the integral, the area between your parametrized curve and the x-axis. Okay.